my brain, see if I can get it. If you can make a question so hard that I can't figure it out, which you probably can do. Okay, so let's switch to the lecture board. And where did it go? It's over here. Okay. March 8th. Okay. If you're recording this, then you see March 8th at the start of it. And I didn't plan it this way, but this is probably a long lecture. Yeah. Okay. So what's the first announcement? You know, after many semesters, the administrators really thought that it would pay off to have SI assigned to the assembly class. Previously, the SI was only working with the freshmen in Computer Science 120. But so I'm here to remind you at 5:15 today, there's an SI meeting at Zoom number 886-115-811-34. Okay. Are we getting close to a midterm time? I think we are.
Okay. I kind of misinterpreted the ticket.
Oh, I'm not sure here. Okay. I'll look it up since I'm going to relax on Thursday. I'll look up the times for our midterm. It's written at the
Oh, does it upload it to the sync API?
last page of the recent description of a program.
That seems more like a testing thing.
Yeah, the midterm is a test on concepts, and then a few days later, there's a test on programming. Okay, the dates are written at the last page of the newest descriptive handout of problem 3. So program 3, I'm going to talk about it right now. That the description has this diagram. I'm just reproducing the diagram. Like usual, we have a driver function, and the handout recommends it be called assessor. Well, you can change that. It really doesn't matter. It's supposed to be assessing property values to tax them. And that in turn calls another function. Suggested name is manager .asm. Okay. And it in turn calls 3 different functions. One of them over here is called get values for the array, get values. And there's one over here. It's we're not going to discuss today. And there's another one over here. It's for another day. Maybe that's for you to do. We're going to work on this one. Get values, and then it calls on is float. And it also at a different time, not the same time, it calls upon AQF. And so our focus is this right here. Okay. So if you see the techniques how to do this piece, then you're going to know how to do all this other stuff, which is actually easier. They don't call any extra functions or anything. So, okay, you with it? Let's jump into the deep water. Okay. Get values. What it's supposed to do is get values means it's supposed to get float numbers from the keyboard from KB and place them one by one into an array. Now, there's some extra stuff. That's the main driving sentence. And maybe we solve this one first, then we go for some add-ons. The first add-on is don't allow invalid numbers into the array. Validate all inputs. And then the second add-on enhancement to this program is do not require that the array be completely filled. Allow the user to input some of the values into the array. Allow partially filled arrays. Okay, and that's where control D comes into play. CNTL plus D. Okay, so what I want to do is not to overburden things. Let's do the basic one up here. Do the basic, solve the basic problem where all inputs are perfect and the system always wants you to fill the array exactly to full. It's not realistic, but it at least is a good start on it. Okay, and then what's the prototype look like? Well, I think it's like long. I should look and see if someone is unmuted. How did that happen?
Professor, did I say all partially filled array CNTL?
All partially filled array. I don't know why allow. Oh, this was allow. ALLOW. Allow a partially filled array and parentheses. We accomplish that with Control D. Okay, now I got better spelling. Okay, so the prototype is, well, what's the name of it? Get values. Parentheses, double, what's the name of the array? I think it was about property taxes. Property, square brackets, comma, long, number of cells. Okay, that helps. For myself, I always write the prototype down. Doesn't matter what language I'm going to use. If it's assembly, I need it anyway. Assembly, I just comment it in the front so I can keep looking at it. But that's what we want to build. Okay, and anything else that's preliminary? I wrote some notes to remind me. Okay, let's give it the first pass. All right. Okay, so program starts down here. How about the early declaration part? Well, we need a global get values. So it can be called from someplace else. We probably have some extern printf extern scanf. And if we think of any more, we'll come back and insert them. Okay, segment data. I can only think of one. I looked at this early this morning. I started writing some notes about it. The only one I think is there is form for floats. dB percent LF. Zero. That look right. I think the BSS is empty. It exists, but there's nothing there. Oh, no, there's nothing there. Okay, BSS. And segment text. Am I under the camera? I hope so. Okay. Segment text, we need the name of our prototype. It is get values. But we put a colon at the end of it. Okay, next jump here. After that, what we always have the same thing, whole bunch of pushes. So there's a block of stuff here, pushes. 16 of them, I think, but copy and paste it from somewhere else, and I think it's 16. Okay, then comes our prototype says you're going to get a copy of an array and a copy of an integer, how many numbers are in that array. So we better take our copies and do something with them. We want to save them in a nice place. Comma RDI. Copy the next one, R14. RSI. Okay, so how about in red? I'm going to mark this one as special because this is the array. That is the array. It's not that it's anything else. It is it. Okay, and 14 is how many potential numbers could be placed in there. So 14 is the count. 14 is the max. Okay, and then every time you have an array, you almost always need a counter that's called the index. And arrays start at 0, so let's start our index at 0, 2. Okay, so R15 equals index. Let's see. No questions at the present time. This part's easy. Okay, so let's see. Do we start a loop about now? We're going to get a number and put it into the array, increment the counter, and then loop around and do it again. So here's this counter and CMP R15 with the max. If the counter has already gone over the max, there's no more room for more numbers. We need to get out of here. So jump greater than or equal to, where are we going to jump to? Finished. That only makes sense. If you have 10 numbers in your array and you've already counted 10 or more, there's no more room for it. So you're just going to follow this trail down to the here and go to the finish part and you're all done. However, if R15 is not up to the max, then we have room to at least put it in one more number. Let's go get that number. And so the looping is started here, you know, and I know we're right here, this little white yellow gap, we're going to have to, that's going to be the top of the loop. but I'll fill in that name in a moment. Okay, so we're setting up. Should we set up a prompt? Okay, move our X 0 output prompt. Prompt says input a valid floating point number and press enter. Something real simple instructions. Okay, I'm not going to write it out because it just wastes time. Let's actually input that number now. So move RAX 0 and move RDI. Did we put an RDI back here? Here it is. Float form float. Okay. And then we're getting ready to call scanf. Scanf needs to know where to put the number. So let's put it on the stack. Push keyword 0. And now the top of the stack, there's a quad word with nothing in it except 64 little zeros. That's where our number is going to go. So we set that as a signal to scanf. That tells scanf to put the incoming number in the quad word that's at the top of the stack. Okay, so here we go. Call scanf. And we're assuming the user has good manners at the keyboard and inputs a nice valid number. So let's take that off the top. The number went on the top of the stack. Let's take it out. Pop. We use our RAX too much. Let's use something else. How about R8? So our number that we want is in R8. Let's put it into the array. Move. The name of the array is up here in red, R13. Am I still in the camera? Barely. Okay, R13 plus 8 times, what's our index is R15. And the number is from R8. Okay. We got it into the array in one slot. If R15 holds 3, then this goes into quad word slot number 3. If R15 holds 0, it goes into quad word slot number 0. It's going into different slots in the array depending on R15. Okay. So we've got one number in the array. We need to increment the counter. INC R15. And I think we have to repeat ourselves. JMP repeat. So now I know we need a place called repeat. Okay, there's the loop. You can see it. It's from here down to here, and it repeatedly gives a line of instructions. It takes in a number. It puts the number into the array. It increments the counter. Goes back and does this all over again. Does it all over again. Everyone got that? You say, yeah, teacher, why is this so easy? I already know what you just told us. Okay. That's probably true, but now we extend it. Okay. So we need to advance this.
Professor, I have a question.
Yes, go ahead.
For where's the output prompt that would go outside, right? I think you clarified right? I just want to make sure.
In my case, I put it inside the loop and it will appear for every number.
Oh, okay.
If you feel better, you can put it before the loop starts and have it one time. And that
Okay.
looks good too.
Okay, sounds good. Thank you.
Okay, so we have two enhancements to make. They are back here. A and B, validate the inputs and then allow the process to stop before you fill the array. Right now, it goes all the way to until the array is completely full. That's not realistic. See, this is an issue here. Okay, so let's go after the stop before it's full. Okay, we're going to solve that one, and then this will get an improvement into it. Before we go there, I got to explain something. Okay, this has to do with same numeric value but different size registers. Okay, let's take the number 6. 6 in its shortest form is 110. Okay, but that's like in a vacuum. We really should specify in what size register are we talking. So if we had 6 in a 1 byte register, it would look like 00000110. Okay, if that's 1 byte. I'm making a big deal out of something really simple. So if we were working with 2 byte registers, the number 6 would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 0, 1, 1, 0. That would be the number 6. Numerically, they're the same, but they don't test as equal in the sense of every bit is equal to a corresponding bit. So they're not equal as registers, but they're equal in mathematical number 6. Okay. So it takes too much to draw it, but we could do that on, say, a 32-bit number. 593. I don't know what the number of bits is. So suppose it's here. 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, something. Okay. So here's 593. But in 32 bits. But you can also make 593 in 16 bits or in 64 bits or 190 bits. You can have different sizes of registers still hold 593. 593. Actually, yeah, if I fill this in with all zeros, I think we get the same answer. Okay. See, so the concept of numberness is a mathematical concept, but storage in bits is a computer programming concept. Here are, discard this. Here are 2 examples of 593, but they're different sizes and they're not considered electrically the same, although mathematically they're the same. So this brings us to a new instruction, CDQE. Okay, and it's on page 79 of the ebook. It doesn't take any operands, no operands, because it only It only works on one register. Why name that one register if it only works on that one? It only works on RAX. Okay, so the C means convert. The D means double. D word, double word, not double flow, double word. Q means quad word. In terms of, this is 32 bits. This is 64 bits. Okay, so when you have in your source program C, D, Q, E, all by itself, it means go to RAX register, split it in half, consider the lower part down here, which is officially called EAX. Whatever number is here, expand it to fill the entire register. So over here was originally junk. And when you're all done with this instruction, then there'll be a complete number all the way across. Okay, and the rule is the numeric value of that 32 is equal to the numeric value of this 64. We don't have to figure right now. We will not take the time to figure out how it does it. Just take it that it will take this 32 of RAX and make it the entire, this 32 in the low half of RAX will become a number in the entire RAX, which has the same value as what it started with. That's the guy, wrap your brain around that concept. Different number, no, same number, but expressed in different numbers of bits. So we're going from a expression in 32 bits to become an expression in 64 bits. That plays a role in what we're going to do right now. Got it, everyone? Okay, I'm going to set this aside. Okay, we have to enhance this so that we can stop it in the middle of the iteration of the loop. We don't want to run it until the array is completely full. Okay, so here we go. Okay, second piece of background information. Can I put it on the back? Is the marker bleeds through. Okay, when scanf is going to execute, your program has executed up to that point, and if you press Control D and hold Control and press the D key down, then scanf puts, it's built into the nature of scanf, it puts -1 into low half of RAX. You can see where this is leading. We just worked through CDQE that works only on RAX, and just by good luck, scanf puts this number into RAX low half. The next thing we'll have to do is CDQE, no operand. Then that -1 is everywhere in RAX. In all 64 bits of RAX. Okay, that's what we're leading up to. Okay, I think at this point, you got this on your video. So I'm going to revise that page right there, and let's see how it comes out. Oops, Okay. First revision is in purple here. That was, yellow was original function. Now we have first revision. Let's see how much we can reuse. Okay, we can still use the global get values. And extern is the same, segment data is the same, segment BSS is the same, get values the same. That whole bunch there is the same. From the extern statements all the way down to, well, actually it keeps going. Get values, push it 16 times, save all these, back up all these incoming parameters, set your index to 0. And we don't change that, we keep that. Etc. all the way down to move R15 to 0. No change. Okay, now we're getting close to scanf. We're going to have some changes. Okay, so right here in yellow, we have a repeat. Let's keep that REPEAT colon. Right below that, we're going to keep that one. Compare to see if the array is full. That's okay. And the next line is still good. Finish. Oh, you know, where did I put the finish? Looks like something's. Let's go back to yellow. I can't find the conclusion. Here, we're gonna. I didn't do. I have to attach the conclusion there. Okay. Finish. I hope that's right. Okay. Yeah, with a colon. Okay. When you're done, you want to send back to the caller how many numbers you put into the array. That's this one right here. And then a lot of pops. Lots of this. And then RET. Okay, I'd forgotten to close it off. Can you get a screenshot? Those of you who are recording this, look, I'm doing a major chunk, 40% of that assignment for you right now. Let's get it all correct. Okay, and then here's how it ends. From first attempt. Okay, now we're improving on it. Okay, so we got to here, and then we're going to output a prompt. I think that sounds okay. Tell the user and put a good number. So PROMPT. And then we set up for scanf. Let's do it again. Good practice. Move to RAX 0. Move to RDI. What was the name of it? Form float. The next one, push 2 words in. We'll still keep that. That's the destination location where the incoming number is going to reside. Move, move means copy, RSI, RSP. Call scanf. Okay, if at that point, if the user, if the human person has pressed Control D, there'll be that -1 over there in RAX. Let's go check for it before we go on. So we're going to take CDQE, which no operation, it only applies to RAX. And then we're going to check RAX, CMP, RAX, are you equal to -1? If that is true, then the human person has just put in a Control D. So then we say, if you're equal, if those two are equal, go to finish. Okay. If they're not equal, we're going to go straight on down and just put the number into the array. Pop R8, copy it from R8 into R13 plus 8 times R15, R8. Is there any more? And then count it. Increment R15 to count those numbers. And then according to the old form, we go back and repeat the loop. JMP repeat. REPEAT. Okay, so it takes us back here and we do it again and we do it again and again. So either the loop stops because you run out of space in the array, that would be this one, or the loop stops because the user has pressed Control D and then it jumps out here. Okay, now let's do the, we have to put the conclusion to it. The conclusion is here. After finish, let's do it right here. Okay, you put the counter into the return variable and then do all those pops. So here's what it looks like. This is the counter right above us there. And we say, move a copy, RAX, R15. And, oh, then we pop all those things. Mini pops. And then RET. That didn't change much. That was the same as the old. Here's the old one that we had. It's still the same. Okay, you got it. That's the in purple. I can't get it all under the calendar, under the camera at the same time. Okay, so that's the purple sheet there. Make a screenshot of that, and then it can finishes off a little bit in the next page. Got that one? Let's see. No questions. Nobody has a question? Okay. So what we have accomplished is inputting numbers from keyboard into an array and being able to stop after first number, after any number of numbers. You're allowed to stop it by pressing Control and a D. That's kind of a nice thing. Okay, what's the next step? We have to enhance it to take care of stupid people in the world who try to break software, in one case by putting in bad numbers. Okay, validation. Okay, what are bad numbers? Bad numbers are 37.5 WR62. That should be rejected as invalid. And things like what's it, 8.222.69. 2 decimal points are not allowed. How about, I had some other strange ones. 8, A, B, 7.9. Somebody's trying to do hex with A, B in there. That's not allowed. See, can you put, oh, spaces are not allowed. 3, 7.9 space 42 is invalid. 16.83 plus is invalid. That's postscript or something. But plus 16.83 is okay. And minus 16.99 is okay. But plus minus 22.5 is invalid. Okay, you got all, that's the idea. We want to throw out the invalid ones and keep the valid ones. Okay, and we have something that does that. That's called the isFloat function, which is already built. Aren't you glad you don't have to write the program for that one? Okay, so let's make the next revision of that same program. It's this purple one. We're going to make the next revision, and it's going to incorporate number validation. Okay, so here it comes. Now this version goes on blue. Let's look at the old one. Yeah, it said there's no change here, and we're concerned with right about in here. Okay, so it starts out global get values. And this goes on with no change. I'll say up to about here, and then we got to work this out nicely. So this keeps going through the repeat and the compare and the JGE. This is the same. No change in here. No change. Okay, now we have to rework this piece about scanf. When scanf, okay, let's go back to here. These users input all this stupid stuff trying to crash software. Sometimes they put in a huge number, 388,888,888,888,999,000,000,125. Okay. We consider that actually valid. We have to let them put in all that number, all those numbers in there, all those digits. So you have to make an estimate in advance. What's the worst case in length of number that somebody might enter? You could say 64 decimal digits, but then there's some idiot who want to try 69 decimal digits. So you have to guess kind of big. And for the other class, I said, why don't we try 256? But why don't we try 512? So we're going to allow storage for 512 of these digits, just in case somebody wants to try it that big. All right, and here it comes. JGE. Here, under here, there's a prompt. You say some nice message, please enter a floating point number using decimal digits and press enter when you're done. VT. Okay. And we start out the same. Move RAX 0, move RDI flow, form float. Now here it gets different. See this one back here in purple? That's making 8 bytes available on top of the stack. That's not enough. That's 8 character long number. We're going to go for 512. So I don't want to count out 512 pushes, but we can increase the stack size by a subtraction. RSP 512. Okay. Now, instead of counting, whatever that is, it's 128 pushes, I think. Instead of counting out all those pushes, we get all that storage available immediately. Okay, now we follow the pattern before. Move, we'll keep this one, move RSI, comma, RSP. Call scanf. Okay. It may be at this point that the user inputs control D. So we're going to have to keep the test to check for control D. Let's put it in. C, D, Q, E. What was it? Compare RAX -1, jump to finish. Okay, if it's not control D, it won't do any, none of this is important. It just go to the next line. Where my the blank space where my finger is. Okay, so our number, let's assume it's not a control D. Our number is sitting on the top of the stack, and it's possibly hundreds of characters in size, but we don't care. We're going to call upon isFloat to check that, to confirm that it's good stuff. Okay, we need to know what isFloat does. So here's its prototype. Bool is float, parentheses, char. It's an array. We call it a string in the old days. An array of characters. It's an old string. So you can see this is an RDI already. Okay. I'm going to call on isFloat, and it'll give me an answer over here, true or false. False comes out as 0. And non-zero is a true. Not 0. Okay. So let's set it up. No. You know, I don't know if we need an RAX. I'll put it in anyway. 0. Move RDI, comma. Our string, our numeric string starts at the top of the stack. And then we call isFloat. It's going to go check that stuff and tell us if, yeah, true, it can be converted to a number, or false, it can't be converted to a number because it has junk in it. Okay, so after isFloat here, the answer is in RAX. That's the return of all integer stuff is RAX. Right there. Okay. Let's find out if false means it cannot be converted to a number. So let's say CMP RAX compared with 0. If that's true, then we're going to say JE to invalid. That's going to come on the next page. Okay. If it's not equal, we go straight down to the next statement. So we had a good number, it actually says. If it gets past this testing for invalidness, then we actually have a good number sitting on top of the stack, but it's in ASCII character form. It's like a string. It's not a true double. But we call upon ATOF to fix that for us. You know what ATOF does? Okay. ATOF prototype returns a double ATOF, and it takes in a string. Like so. So here's the RDI. And this will be XMM0. Isn't that great? You ready, everybody? Okay, so is it still in the camera? I think it is. Okay, we got past the test and we have a good number there. So we're going to, let's do the setup. I always throw this in extra, but some students say that sometimes it works without it. That's probably true. Move RDI, comma, top of stack. Okay, and then we're going to call ATOF. And ATOF takes that string and converts it in a IEEE floating point number and puts that number in XMM0 for us. Comment here is number is in XMM0. Okay, so let's go get it and put it into the array. Move MOV, so to read that, into R13 plus 8 times R15, comma, XMM0. Okay. We got it in an array. That's good progress. How does that compare with the previous version in purple? That's oh yeah. It's here and we copied into the array, and then here it is. It's time to increment the counter R15. That's like R15 plus plus. We increment it, and then we go back and repeat this loop. JMP to repeat. And do we have a repeat in this blue stuff? Yes, we do. It takes us all the way back to here. There's supposed to be 2 dots there. And then it checks to see if there's still room in the array for more. And if there is, then you get a prompt, and then you input more stuff. Or if you happen to put in a Control D, you will jump to the finish conclusion. They got to figure out where those, yeah, put the finish in here. Is it directly below here? I think it is. I just want to check this. Here's finish. Did we have another jump somewhere? When it's full. Oh, way back here. When it's full, you jump to finish. All right. And in the old one, where was finish? Finish was. Oh, yeah. Oh, yeah, yeah. See. Yeah, here. It's coming clear. Okay, so here's finish. F-I-N-I-S-H colon. To finish off, we want to send the counter of numbers back to the colon place. $15. And then I don't think there's any more to do. We do all these pops. 15 pops. And say return. RET like that. I think that's
What
it.
about invalid?
Where do we get the? Did I leave that out? Oh, here. Oh, yeah. I see your point. I could replace okay, invalid. Okay. Yeah, we'll fix this. This is not hard. If someone inputs a invalid number, what do you want to do? Do you want to just turn off the program and say you have to run this whole program again? Or do you want to give them a second chance where they get a second chance to input the number? That's where we have to decide where to place this jump to invalid. If you want to give them a second chance, why not? Here, I'll give you a solution. To give them a second chance, we'll send them back to the prompt and they'll see the message, enter a floating point number, press enter. We'll send them back to here and they'll go through this again. And if they're invalid again, they'll go through it again. So here's one answer to that. It's the gap's too small. It's in the gap between prompt and this other box. So you squeeze it in there. It's called invalid with a colon. That's the solution that keeps the person entering number after number until he finally gets it right. Okay, or Control D if you can't get it right. Oh, that's a pretty good solution. The other one is you could put invalid down here next to finish. Let's see. You can do that too. You're allowed to put, by the way, you're allowed to put two of these side by side. You could put invalid here. Cool. Invalid is not an executing statement, it's just a marker. So if you jump to here, it will fall through into here. That's where you don't want the person to continue. You're making them shut down the program. You decide when you program this. I like the first one, but you decide what you like.
Can we just like inside invalid, can we just put like jump to repeat?
Yeah, I think you could. Right here. Or jump to repeat. So what's the difference? Almost no difference. If you jump to repeat, you do the test again to see if there's room in the array. There's no harm in that. We assume that if somebody inputs invalid, it never gets into the array anyway. Therefore, doing the compare test to see if there's still room in it isn't really necessary, but it doesn't do any harm either. Yeah, this would work. Just the logic would be performed exactly the same as if you did this. Going to repeat, you're going to check to see again to make sure there's space available in the array for the next number to come in. You got everybody? I think we're done. Okay, this is the end of get values. And it's the biggest single piece out of that whole program. Let's go back to the original, many pages back. That's how we got here. Okay, here's the diagram. Okay, so in manager, in the BSS segment, they declare some array, property. Reserve, keywords, 25. There's the array. And when manager calls get values, it passes the array as the array itself as RDI, and it passes the 25 as RSI. So there's a little setup going on. Move property to RDI, move 25 to RSI, move 0 to RAX, call get values. All that takes place inside of here. The array travels along, get values uses it under the name, under a different name. So when it arrives here as RDI, it was immediately copied to R13. R13 received the value of RDI. And this worked with R13 precisely as if it were the word property spelled out. It just used that as the array itself. And when it's all done, the new numbers have been placed in the array, but manager already has them. Manager created property and owns property. With this one putting numbers into the array, manager has it instantly. There's no pass back time. What manager doesn't know is how many numbers have been placed into the array. And so this one has to have a return through RAX. RAX gets carried back and copied back. We say copied back, but that's the idea of it, to manager, because I think the next one is to display the values. Display. This one needs to know that number in order to display the exact number of values from the array. That number is probably less than 25, like 8 or 10 or 12. Okay. Passing forward, we call it is two things: the name of the array and the number of cells in the array. Passing in the reverse direction is the count of how many were placed into into this function. How many numbers this function placed into the array that manager already owns. Okay. How are we doing with this? You got it all? Okay. So this, in the coming days, in the next 48 hours, everyone sitting here should do a scaled down version to see it works. Accessor is int main. Does accessor return? Does anything get returned to it? We'll have to look that up. Let's say, I don't know what number, integer, long, code equals minus 99. Code equals manager. Output the code. Return 0. Okay. there's no welcome message yet, but there's a skeleton that you can do quickly. Manager, we want a skeleton so you can call get values. Manager needs a segment, BSS, property, reserve 25, segment text. What's the name of this one? It's manager. Colon. Okay. Here's all these pushes. There's you back up the two things coming in. Move. Sorry, no, nothing's coming in. See this box right? This little thing is empty, so there's nothing coming in. This set up immediately and call get values. So move RDI property. Move RSI 25. Call get values. Um, 16 pops and return. There's a skeleton so you can test your get values. That's enough to get a first run test. Make sure it's error free. You won't see your numbers appearing until you program this one later, but at least you can say I got something that executes. Then you can fill in the bricks to build the house later, piece by piece. Okay. Okay. I got one. I'm going to change the subject for about 15 minutes, unless I see questions about this. Okay. Let me go to this side. Okay, I'm done with these. The other class, the other section of 240, we took the last remaining time and did one practice problem. You ready for a practice problem? Okay. So let me think if I remember it. Let's take 89 and 3/7. That's a 3. 89 3/7. What is that in IEEE? This is so your brain hasn't forgotten how to do it. Do these kind of exercises. Okay. 89. 89 is 164. In your head, you subtract those, and there's a 25 left over. Plus 116. You subtract 16 from 25, and there's 9 left over. You subtract 8 from 9, and there's 1 left over. And there's the 1. So 89 is 1011001. Okay. Remember how to do the fractions. You solve these by separating a whole number part from fractional part. 37, not 37, 33 sevenths. We multiply by 2. Uh, 5 7 times 2 is 10. 1 plus 3/7. 3/7. Is 1 plus, that's 12, 7, 5 sevens. Okay, so we can stop here because it's starting to make a pattern. See, that block is starting to show up again as a repeat block. So we don't need to go any further. Now we know that the fractional part, 3/7 is 0.011011011011011. Just in the camera range, 011 dot 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 forever after. Okay, repeating binary number, not. I guess it's in decimal. It's repeating decimal also. Okay. Now we have put all these together. Let's combine the two parts. 89 and 3/7 is 1011001 dot 0110110110111, etc. And that's not scientific. You already know that. Where's my, I lost my red marker. There it is. Okay, to be more scientific, it should be about here. That's a shifting of six places. That's really strange. Okay, so it comes out to be 1.0110011011011 times 2 to the 6. Okay. This is a bunch of easy peasy stuff for you. I want to take a break on next class meeting, like Thursday. I'll sit back and then you ask me hard questions about the midterm coming a week later, and we'll see what you need to know. Okay, so now we have a true exponent, number 6. 6 equals true. And we like to add bias number. Isn't that a nice number? You all like that one? That equals bias. And then you add f plus 6 is, you count on your fingers. F plus 1 is 10, 11, 12, 13, 14, 15, finger number 6. So I write 5 here and carry 1. 1 and F is 10, so I write 0 and carry 1. 1 and 3 is 4. We got it. That is stored exponent. Okay, it's coming out really nice. So in our number, and once you get really good at it, you just skip the binary intermediate stuff. But I'll do one more time in binary. So 4 is 0, 1, 0, 0. And 0 is just 0. And 5 is 0, 1, 0, 1. Okay, then that's all exponent. From here, I have to go up here and take groups of 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Did I get this in the right place? I hope so. 1, 2, 3, 4. Wow, looks tricky. Oh, this is going to get something messed up. Okay, so I'm going to copy that. If I use red, it will distinguish mantissa from exponent. 0, 1, 1, 0. Next one over is 0, 1, 0, 1. The next one is 1, 0, 1, 1. And next is 0, 1, 1, 0. And next is 1, 1, 0, 1. Wow. This is now amazing. There's no repeating pattern yet. There has to be, but we just can't see it. Okay. The issue is I have to make this longer. Okay. So how we get there is from up here, a 0 and 2 ones, a 0 and 2 ones, a 0 and 2 ones. So here is a 0 and 2 ones, then come 0 and 2 ones, 0 and 2 ones, 0 and 2 ones. And I'm running out of paper. Okay. Now I have to group them by fours. There's a 1, 2, 3, 4. 1, 2, 3, 4. Okay, did we get any better? So that's a 5, 8, 9, 10, that's 11, B, and that's a 6, and that's a 12, a D, it looks like. And 1, 0, 1, 1. 8, B again. And a 6. Okay, let's see if I can write that over here. So where did we get there? There's that one, that one, that one, and that one. And then this one. And then hidden here is 1, 0, 1, 1. 1, 0, 1, 1. And then hard to see, but it's 0, 1, 1, 0. And then there's more stuff coming. I wonder if we can interpret that. Okay. Right here, this is 6. That's a 5. That represents in decimal 11, which would be B. That's a 6. That is D, D, I think it's D. And that's a B. And that's a 6. And we don't know what that one is. I shouldn't. You know what? I think it's showing up. See how that D, this is an incomplete number. I won't have it here. Well, if I went one more, it would be 0, 1, 1, 0, 1, 1, 0, 1, 1. So it's a C, it's a D. Because it's, I can see it up there, 0, 1. Okay, is this a pattern? I think it is. So there's a 4, 0, 5, 6, 5, B, 6D, B, 6D, B, 6D, B, 6D. Okay, we got it, we got it. Okay. Final answer. 4, 0, 5, 6, 5B, 6D, 5B, 6D. And then it's B6D, 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 B6. And outside the register, there's a D coming. But the register is full. Okay, class, what do I do with that D out there? I should just erase it. I should eat the D and lose part of the number. And you're really not sure? Okay, can I leave that for a test question? So your assignment is to go run one of the online calculators and see what that says as the answer when you have extra D on the end. Okay, and I'll put this on the test. Okay, we're done, class. Can I answer any questions about anything this semester that has happened? Either programming or just general knowledge. Like, well, what are the parts of a von Neumann computer? Or when can we all purchase a quantum computer? Stuff like that. Or what is my last name in Little India? You'll see all work well. Yeah, yes, Greg. I phrase it this way. You guys show me enough so I'm convinced that you know what you're doing. If there's a question, what is 89 3/7? And then somebody comes down here right here. Here it is, professor. It's just this number. I got it. See how smart I am? And then I give him a 0 because this guy obviously just went to a calculator and looked it up. Getting knowledge of how to press buttons on a calculator doesn't get you any points. So you have to show me not every single intermediate step, but at least enough of it that I say in my mind, this guy really knows what he's doing. He knows the algorithm. So the answer to Greg's question is yes, show me enough. Show some of it. And we all know how to use calculators. That doesn't interest me. It's just kind of boring. I like to know that you know how it works inside, not just how to use it. Calculators do this work. That's IEEE conversion that you just saw. Calculators do that work. We should know how they're doing it. You're welcome. Okay. I'm going to pause here from lecturing. I'm just going to hang out and be present until almost 4 o'clock, like most other days. I wish you have a nice evening. Once you could drop in and see the SI leader in an hour and a half from an hour and 15 minutes from now, and see what kind of perspective he's teaching. It's good to see another style of presentation other than just me. See how he presents this same solution, or whatever's going to be presented. It can't hurt you. Now that we're coming close to midterm time, it's like 10 days away. Okay. Like I said, I'm just going to be quiet now, and I'll be here. If you want to ask me anything, get my attention, and I'll work with you. Okay, well, there it is.
Professor.
Yes, I'm here.
So in the loop with the input validation, kind of confused on why why you did the subtract RSB by 512.
Yes, I can tell you. Let me find clean paper to draw a picture of that. Hold on. We'll do this. Uh, Okay, here's the backside. See the subtracting in the early version of the same algorithm, same function, there was a push keyword 0. Okay, the Q makes it 8 bytes. So the stack went from this picture, there's a bunch of numbers in here, 129, 79.6 and 83.2. It went from that picture to this picture.
Okay.
0. There's the extra one. Okay. So what happened to the address? Here was the RSP was at this place originally. And then it's at this place. What happened was because of the 8, an 8 was subtracted from RSP to get to here. If you checked it out, the number would look like 4888. And then you look at this one and it's 4880. Okay. So a new quad word subtracts 8. Well, I want to add to the stack about 20 new quad words. I could go push quad word 0 and count it out 20 times and accomplish the same thing. But why not just start from here where there's 79.6 and 129. And here's RSP, it's just a big integer. And I'll subtract 512 from there, whatever that comes out to be. And suddenly I have this picture. 79.6 is still here and 129 is still here. And it's added all 512 bytes of new space here, 512. In one
This is pretty
fell,
much create space for,
that's right. It creates
Okay.
space of 512 bytes on the stack. What you don't want to do is subtract something that's not evenly divisible by 12. That gets into a mess. But 512, I didn't say that right.
could you explain that, like being divisible by 512?
I said it backwards.
Oh, okay.
8 is divisible into 512.
Oh, I see, I see.
Yeah, then it's a
Oh,
good,
okay,
it's a good subtraction.
okay.
You don't want to subtract like 7.
Right.
That's a bad one. But if you're subtracting a number that's divisible by 8, you're good to go.
Okay.
And it'll just create a lot of space.
So what would the difference be if you were to do like a subtraction of, say, like 1024, or half of 512 would be
Yeah, it did
256.
256. It would go halfway down.
Okay,
You had these 2 existing numbers, and it would add 256 of new space here.
okay.
That would be a subtract 256. What if you subtracted 2? I'll make a point of this.
Okay,
If you subtracted from RSP 258, it's not divisible by 8.
mhm,
Then your stack has 2 old numbers, whatever they were, 12 and 79. And then it grows down here and has a crooked corner in it.
oh, that's not good.
That's not good. You now want to push a quad word, and it's half dangling here and half over here. It's just bad.
Yeah.
So subtracting any nice number divisible by 8 works just fine. It's equal to a whole bunch of push quad word zeros. You You create a whole bunch of space.
Okay, so, so like, how would you like say like, so you have that amount of space, how do you like reset it back to 4,888?
Oh,
Do you just do a pop
no, you should do
Or-
an add.
or add?
256.
Okay, sorry.
If you did this subtraction, then later
Okay.
on you have to add RSP 256.
Okay.
Yeah.
So in our assignment, so you did subtract 512, so would it make
hope-
sense if you did, if you add at the end or?
I hope I added. Let's go back and look at the old history, and that would be a blunder if I didn't.
Oh,
Oh, no.
I don't think I remember.
Uh-oh, uh-oh. I think this blue was the recent one.
Yeah,
Oh,
yeah,
wow.
I don't remember because I was taking notes, so.
Hey, you're pretty, you led me to the problem. I forgot to do that. Right in here, after the finish, should be an add. RSP, the same number we subtracted
Just 512.
512.
Okay.
All of you who are still left, fix your notes to take into account. We have to put RSP, the top of stack, back where it was, and the failure will happen here.
I see.
RET can't execute unless the stack is back in the original state it was when the function started running.
Okay.
Okay.
Yeah, I was confused about that a little bit. Okay, that makes sense. Thank you.
Thanks for bringing it up, though.
Yeah, of course.
Okay.
Professor?
Yes, I'm here.
Oh, I believe you have a question in chat.
Oh, I wasn't looking closely. Oh, I see. Yeah, is float and ATOF are functions that you borrow from someplace else. And what for? Oh. Okay. For ATOF, we don't know. You don't have to compile it. It's in the public library. You just have to declare it as extern. And then the linker knows where to find ATOF. The words stand for, A is for analog, TO is for 2, and F is for float. So in old days, they called a string of digits an analog string or something like that. Is float, you should look at the class website and see if it already exists, and then you'll be able to see it, what language it's written in, C++ or C. Or some people last semester posted is float in Discord. They told me that they had posted it there. So both of those are functions that you shouldn't program yourself, but you should borrow. You need to go borrow is float. A lot of students have that one. ATOF is built into C++. And I don't know what language it's written in because we're never told. You can look in the index of a C++ book and you can see ATOF reference there. What those is used for and which part of get value is it called in? Yeah, it's in here on my page in front of us. There it says call ATOF, and that came this whole 2 pages together. That's get values. There's a scanf, blah, blah, yeah. So there's your answer. There's an is float. I lost my marker. See that one of the red one. Okay. You asked where do you use them? Here it's in use. And here it's in use. It's needed 2 places to finish its job. And we can see that in the diagram. If I can put my hands on it, I'll put the diagram here. I don't know where to do it. I'm still looking. Oh, it was this one. Get values calls its float at one place, and it calls ATOF at another place. Okay. You don't have to program these. You just have to go find them. Ask your classmates. Some from the morning class say they already done those 2. They've already used those 2. Missed the part. Just want to correct one. Oh, that's okay. Yeah. Okay. Yeah, you got it. Here's the whole is get values program. Kind of long, but it's under. That's gotta be under 20 statements, maybe. If you can't find is float, ask the SI leader. I'm sure he saved it when he took this course. Yeah.
Professor,
Yes.
for, I just wanna make sure, cause like, for push keyword, 0, to negate that, do you do pop racks or?
Oh,
Cause I know like you subtract with push keyword, so you,
yeah. That was in the old version.
oh,
It got removed later when we did a subtract 512. The early version had a push quad word 0 here.
mhm.
Okay, and then later down, I had to pop that
Oh, with the R8, right?
with an R8.
Okay.
Yeah.
Could you have done a racks instead, or would that?
Yeah, you could have used racks to do that.
Okay, okay.
It was just a free choice. You could have used R9 or R11. It would be okay.
What, so when you do that, pop R8, how does it, what's it called? Like negate the push quad word?
Well, these 2 right here are opposites of each other. See?
Okay, push and pop, that's right.
Yeah. For every push, there has to be a corresponding pop, or else the return statement won't execute.
Okay,
So here's the match.
right.
If you have 3 pushes somewhere, you got to find 3 pops to offset them, else you'll get a segfault.
I see. And, like, why is it that you could choose whatever, R, like, say, like R8, R9?
Oh, it's simply that I can choose any register that I'm not already using.
Okay,
So I'm using R13, R15. I thought I was using R14 is in use.
okay,
So I could pick R12, R11,
okay,
and so on. Just anything that's not currently being used in the program.
okay. So would it be like more like would it make sense more to use R8 instead of like anything like that instead of racks or
Hmm, just my personal view is that Rax gets used repeatedly in so many
okay,
places. I wanted to make sure that what I'm popping is not overriding something important.
right, okay.
So
Yeah,
this has never been used in this program, so I used it.
okay, that makes sense because like I've been for the past assignments I've been struggling with that. I keep getting core dump errors
Yeah,
because of popping racks.
that could be, the Rax gets so reused so many times.
Yeah.
You may be overriding something important in it.
Yeah.
Uh, So spread the work around.
Okay.
Try other registers sometimes.
Okay.
One last comment about that.
Okay.
In our book, look, what do they call them? Stable. There's some place in the book, there's a page where they list the stable registers.
Okay.
I'll have to dig that out and present them in a lecture sometime.
Mhm.
Out of all the R type registers, there's like 6 of them that are very stable. You can really trust them. And then there's the other ones that are less trustworthy. So uh, remind me next class meeting. I'll look up
Okay.
that
Yeah.
list. And we'll talk about them.
Okay. I'll put that as a reminder.
Okay.
All right. All right. Cool. All right. Thank you for answering all my questions. All
You're welcome. I'm glad to do it.
right. I'll see you Thursday. Have a good
Yeah,
day.
yes. See you Thursday. Okay. Did you teach how to set up, get, and show? Because I saw the function prototype, but not. Oh, there's main doesn't have those functions. Main has, I wrote main here somewhere. Here's a skeleton of main. It only calls manager. It doesn't call his float or ATOF or anything else. It only calls that one. And it needs to have a prototype up above. And let's make it right now. Long manager, parentheses, semicolon. Um, and I'm trying to remember, I think it has an extern in front of it. Now, more I think about it, I'm sure it does. So it's only, main is only going to call one function with no parameters, and that one function needs to be named here above main itself. And main doesn't know anything about get values or is float or ATOF. That is the setup right there for calling manager. And that's where's the picture of all that is this one. This diagram shows that the main up here only calls this one, nothing else. And main doesn't know that these others exist even. It says that. Okay, this one is assembly. You don't use prototypes the way main did. So this doesn't, it just says, this one just says extern get values. Get values. There's no such thing in assembly as a full prototype the way we have it in C++. And what is the, show? Oh, did you do the screenshot? Here's the whole thing. I gave it to you. What's inside of get values? That's what it took us an hour and 15 minutes to show it. I lost the page. Let me see. No, that's not it. Make a screenshot of that. That's the whole thing. Save yourself an hour of work. Okay, that, yeah, that's it. That's gets values. It's all its code right there. Oh, lots of people video. I hope you're videoing. If you're videoing, if you're recording this whole lecture, you got how it was developed. Missing the. There's 3 lines of conclusion. I can't find it now. That's there's the mini pops are at the bottom, and then a return. It's off the page.